Suppose you're learning about the physics of heat and mass transport. You know, stuff like diffusion, fluid flow, or heat conduction. When learning about molecular diffusion, you'll encounter a property called diffusivity, which is what I want to talk about in this video. Now, I'm going to run quickly through a lot of physical science in the preamble. If you don't catch all of the details, don't worry, they're not the main point. But I didn't know of a good way to set up the topic I wanted to cover without at least touching on the truckload of background behind it. I'm also not going to be doing any mathematical derivations or solving any differential equations, but it would help if you've had at least some beginning calculus and know what derivatives are. Let's say you're looking at two separate liquids, like milk and coffee, before it's evenly mixed in. If there's a difference in concentration, d phi, across a small distance, dx, then there will be diffusion of milk from high to low concentration. The diffusion flux, J, how much milk diffuses across a cross-sectional area over time, is dictated by the concentration gradient and a property called diffusivity, D. The higher the diffusivity, the greater the diffusion flux. The diffusivity depends on temperature, the substance that is diffusing, and the medium it's diffusing through. Diffusivity has units of meters squared per second, length squared over time. Diffusion behavior is codified in Fick's laws. This is Fick's first law. Fick's second law says that if there's a curve in the concentration gradient, then that curve will tend to flatten out, again mediated by this diffusivity parameter. This makes sense. Suppose you have a concentration profile that looks like this. Since the left end has a steeper concentration gradient than the right end, the diffusion flux going in will be greater than the flux going out, leading to a net increase in concentration in this space over time. The second law can be derived from the first given mass conservation. Now let's talk about heat conduction. We're avoiding the added messiness of convection and fluid flow for now. This is the heat conduction equation, sometimes called Poirier's conduction equation. It says that if there's a temperature gradient across a material, then heat will flow from the hot side to the cold side at some rate dictated by this parameter K, the thermal conductivity of the material. K has units of watts per meter Kelvin, or power divided by length and temperature. The conduction equation is analogous to Fick's first law, and there is a heat conduction analog to the second law as well, called the heat equation or the energy equation. Here, rho is the density of the material, and C is called the heat capacity. The heat capacity is another material property that tells you how much energy it takes to heat up 1 gram of stuff 1 degree Celsius or Kelvin. Basically how much thermal energy a material can store for its weight. So far so good, right? Are you ready for the fun part? This ratio of constants, thermal conductivity divided by density and heat capacity, that can be labeled as alpha, and is called the thermal diffusivity, with units of meters squared per second. Alright, no time to waste. Let's talk about fluid dynamics. The viscosity of a fluid is a measure of its thickness, so to speak. Like if you rub a bit of honey between your fingers, you'd notice that the honey exerts more resistance than other fluids like oil or water. The force, F, that you need to apply with your fingers depends on how fast you move them, U, the area of contact, A, the thickness of the film, Y, and the viscosity, eta. Viscosity is often reported in units of poise or Pascal seconds, pressure multiplied by time. The next step is really very intuitive. Rewrite this equation in terms of shear stress and strain rate, apply momentum and mass conservation, add pressure and gravity forces, and just like that, you get the great granddaddy of fluid dynamics equations, the Navier-Stokes equation. Now, the equation as written here applies for Newtonian fluids, those with constant density and viscosity. The value we introduced as viscosity is sometimes specified as the dynamic viscosity. Dynamic viscosity divided by density is called the kinematic viscosity, or the momentum diffusivity, with units of meters squared per second. This symmetry didn't escape the notice of a couple students in our undergraduate class, and one of them raised their hand and asked the professor, "What is diffusivity?" The professor was good-natured, but his answer was a bit unsatisfying. Something like, "It's similar to viscosity in that it determines how easily momentum is transferred. The general units of diffusivity are meters squared per second. Just divide dynamic viscosity by density and there you go." Now, he was a good professor, and I don't blame him at all for a lackluster answer. I did some digging to try to answer this question for myself, and most physical science texts don't offer any better explanation. They don't address the source of the pattern. For that, I had to dig a bit into the mathematical model. I want to come clean up front. A sizable fraction of the audience that might view this video is definitely better at math than me, but my goal is outreach, not rigor. I want a description of diffusivity that I can offer physical scientists that goes just a bit farther than diffusivity determines the speed of diffusion, without overwhelming them with jargon or rigorous derivations. But my field of expertise is neither transport phenomena nor mathematics, so I understand that I risk being off base or inaccurate. Therefore, you should understand that I'll need to start this off with a stiff drink. Imagine someone who is completely drunk, attempting to walk anywhere. He spins around and starts heading in a random direction. After walking for a short distance A, he stumbles, spins around, and continues walking in a new random direction. After walking another segment A, he changes directions again. This process repeats many, many, many times. After he's finished walking, where does the drunkard eventually end up? With a small number of walking segments, the drunkard won't get too far from his starting point. He'll usually end up some distance away from it in a random direction. The probability of where he ends up follows a normal or Gaussian distribution. As the number of walking segments increases, the probability distribution spreads out. The drunkard's walk is also called a random walk, but I like starting out with the drunkard because it makes for a more entertaining analogy. There are many different types of random or stochastic processes, but we'll only concern ourselves with a handful related to the random walk model. At the most restricted end is a lattice random walk, where each iterative step can only land you on a set of specific adjacent locations or grid points. At the other end of the spectrum, both directions and distances of each step may vary, so long as Gaussian statistics are adhered to. This is called a Wiener process after mathematician Norbert Wiener. Both of these processes can be used to model diffusion. A Wiener process is a better model for things like Brownian motion and fluids. A lattice random walk applies to something like diffusion of voids or impurity atoms through crystalline solids, where the atoms are arranged in an ordered lattice. Differences between the two processes are only important if you're looking at molecular scales or very short times. Otherwise, at human sizes and longer times, both processes converge to Gaussian statistics. To understand why these processes work for modeling physical diffusion, let's look at the list of requirements for the Wiener process. 1. The object starts at position 0 at time 0. 2. The path is continuous. 3. Future steps are independent of past steps. 4. The process is Gaussian. The first rule is a technicality, a bit of initialization or normalization, as you might say. No need to go over it for our purposes. Let's go through each of the other rules and see how they apply to our energy and mass transport processes. 2. Continuous path. There are two implications of the word continuous here. The first idea is that the object can't instantaneously teleport to another location. And before you ask, well, what about quantum tunneling? Note that I said instantaneous teleportation. Even quantum tunneling is limited to the speed of light, or more exactly, the speed of causality. So it's still technically allowed, even if unlikely. But there is a second interpretation of continuity that I think is pertinent. Others might be more familiar with a different term. Conservation. The drunkard does not spontaneously spawn a clone of himself, nor does he die. In the analogy, one situation is more likely than the other. Both are horrifying, and thankfully, we can mandate that neither happens. On Earth, mass and energy are conserved. Whole atoms do not regularly pop into existence or annihilate. For thermal energy, there can be heat sources and heat sinks, such as friction heating or chemical reactions, but these are external to the heat itself. When we talk about conservation, we mean that the packet of thermal energy itself is not responsible for spontaneously generating more thermal energy out of nothing. 3. Past independent. It doesn't matter where it's been previously, the object can move back and forth however it pleases. Again, pretty straightforward to accept, although this prerequisite is more flexible than you might think. 4. Gaussian statistics. Now, this initially might seem like flawed logic. Diffusion is Gaussian because it's a requirement for the Wiener process? Actually, no, the causality goes the other way. The Wiener model is forced to obey Gaussian statistics because that way it better matches real physical processes. At the risk of going down a meta-question rabbit hole, I'll just briefly touch on why the Gaussian distribution applies to diffusion, as opposed to a different type of statistical distribution. There are 2 ways you can think about it. 1. The Gaussian distribution results from satisfying the conditions of the Central Limit Theorem. Given any random process, like a dice roll, even with weighted dice, as you add up more and more rolls, the results approach a Gaussian distribution if the dice are independent of other variables and do not interact with each other. 3 Blue 1 Brown Ori has some nice videos on this if you haven't seen them already. But let me stress the leap in conceptualization we have to make. We have to imagine molecules or packets of energy as randomized objects, like dice or balls in a pachinko game. And diffusion is an emergent phenomenon of an inconceivable number of these dice rolls. It arises entirely from random processes, not driven in any particular direction. Any single molecule could go in any direction, but matter appears to diffuse from regions of high concentration to low concentration because there are simply more molecules available to travel from a crowded side to an empty side than there are to travel the opposite direction. This is the thermodynamics version of God playing dice with the universe, before quantum mechanics came along. And folks like Ludwig Boltzmann garnered significant pushback for it. One more note, the independence rule is sometimes violated in real physical systems, which leads to deviations from ideal Gaussian behavior. But in most practical cases, those deviations are negligible. 2. The Gaussian distribution maximizes informational entropy. Informational entropy, or Shannon entropy, is a measure of uncertainty in the values of a variable. And, important note, it's closely related to Boltzmann entropy. But that topic is outside the scope of this video. There are already a handful of videos I recommend that give a nice introduction to the topic if you're interested. The upshot is that you could say that diffusion follows Gaussian statistics because of the second law of thermodynamics. Alright, getting back on topic. What does this mathematical model look like? Imagine a temperature profile that starts out as almost a delta function at time t equals 0. Basically, just a single narrow spike. Analogously, you could also think of it as the exact starting position of a single diffusing molecule. The solution to the heat equation, also known as a heat kernel, looks like this. The evolving temperature profile looks like a Gaussian bell curve that steadily spreads out over time. The variance, a measure of how spread out the distribution is, depends on time, diffusivity, and the number of dimensions. Because, theoretically, each diffusing object acts independently, you can then imagine any starting temperature profile as a sum of a series of delta functions, a whole bunch of spikes. Or if you're talking about molecular diffusion, the starting concentration profile is the sum of the positions of each individual molecule. As time moves forward, the evolving temperature or concentration profile looks like lots of spreading Gaussian bell curves all added together. So, diffusion is the result of a bunch of random walks, and therefore follows Gaussian statistics in the ideal case. And Gaussian statistics goes hand in hand with the heat equation. And don't let the name fool you. This partial differential equation applies to multiple forms of diffusion, not just heat. All of these different types of diffusion are characterized by their own diffusivity parameter. But all of these parameters have the same units because they're all modeled as random walks. And the random walk model doesn't care who's doing the walking. so long as they maintain continuity. The random walk model highlights what diffusion processes are actually based on at the microscopic level: random scattered motion of large numbers of discrete quantities. Now, it is easy to visualize molecules moving in a random walk and accept that model. Thinking of thermal energy in terms of discrete quantities or packets that also move in a random walk is atypical, but it's not uncommon. Thermal energy is sometimes conceptualized as packets of molecular vibrations called phonons. It's similar to how we can think of light as packets of oscillating electromagnetic fields called photons. What is rare is to think of fluid momentum in the same way, as conserved, discrete packets that are subject to diffusion. And the result is more complicated because momentum is a vector quantity while heat molecules are scalar quantities, so to speak. Yet, that is a valid way of visualizing what's going on, at least for low Reynolds numbers. It is movement that is itself moving. This might require an illustration. Imagine you're suspended over a large, still body of water, and you use a paddle to gently push some of that water. The patch of water you push starts off moving as a unit, but the forward momentum, while it is conserved, diffuses quickly. And remember, it's the momentum wave itself that's moving in this manner. It's not necessarily the same cluster of molecules moving forward. Like billiard balls knocking each other around, the molecules are passing this momentum off to one another. This momentum diffusion dissipates kinetic energy, and it depends on the viscosity, how readily the molecules transfer velocity to each other through collisions and cohesion, and inertia, how slow the molecules are to accelerate when pushed. Now that I think about it, perhaps the problem isn't that we lack a good description of the diffusivity parameter. It's that we don't often get a generalized description of diffusion that encompasses more than just molecular or thermal diffusion. So that's what I've attempted to provide here. Diffusion is the randomized scattered motion of something, typically a packet of matter or energy that follows conservation laws. For example, that something could be molecules, or phonons of heat energy, or bits of forward momentum in the case of fluid dynamics. Diffusive motion follows Gaussian statistics in the idealized case, and eventually leads to homogenization or flattening out of concentration profiles. The diffusivity parameter characterizes the speed of diffusion, how fast the profile flattens out. It is important to note that this is not the only way to think of diffusivity, nor is it necessarily the most useful. For example, let's quickly review some strictly mathematical interpretations of the heat equation. A first derivative gives the slope of a curve at a certain point. The second derivative gives the curvature, whether the line curves up or down, and how tightly it does so. Thus, the heat equation says that curves in the temperature profile will flatten out over time at a rate defined by the diffusivity, and sharper spikes flatten out faster. Or you can consider the Poirier solution to the heat equation. That is, imagine decomposing the temperature profile into a series of cosine waves that each decay at different rates depending on their frequency. Or you can think of diffusion as lots of infinitesimal averaging operations everywhere along the curve. All of these descriptions are correct. They all give the same answer, and none of them are objectively better explanations than any of the others. These mathematical descriptions are more proximate to the effect of the physical phenomenon, and allows you to quickly intuit or predict the end result of any given situation. The model of diffusion, as random walk motion of a conserved quantity, is more proximate to the cause, the reasons for why the phenomenon arises in the first place, which helps you to understand why certain materials have the properties that they do, and what could possibly be done to tweak those properties if you wish. For diffusivity, I felt that this latter description was lacking in traditional instruction on this topic. So that's my attempt to explain diffusion and diffusivity. If you're still lost, don't worry about it. You might have noticed that I referenced a bunch of other videos as well. Links to all of them are in the description. Mass and energy transport phenomena are incredibly complex. Consequently, I was originally going to add a list of extra credit notes at the end, but one of those notes ended up giving me issues. So it's getting its own video, and I may stick the other notes in there as well. Keep an eye out for that if you're interested. I'll try to get it out sooner rather than later. Anyways, thanks for watching.